Okay, good morning, everybody, and thank you for this invitation. I am a physicist, and I will speak like a physicist of how can we improve communication, how can we use less energy to send more information in any kind of media. And because my background is waves, I am not working only on microwaves, but I work also on sound, on ultrasound, on optics, and I will show you how in all this field, the concept of intelligent surface is a kind of revolution. Let us begin by a first slide. Okay, here you see different kind of reconfigurable intelligent surface that are called now RIS. On the left side for RF signals, it's a kind of mirror that you put in a room made of many pixels, and each pixel can be in two states, and by changing the state, the mirror changes the way it reflects the waves. It can reflect by changing the signal or not changing the signal, and you will see that this can be very useful. This is the left part of my slide. I try to look if my... And on the right part, you see the same concept for sound. It is a room where you put an intelligent surface and you can play, and you will see very strange things that you can do in a room. This was done, RF Reconfigurable Intelligent Surfaces. The first one was built in 2013 in our lab. And for sound, it came later in Hong Kong, 2017. But in optics, the concept of reconfigurable intelligent surface exists for a relatively long time because it is what is called spatial light modulator made of liquid crystal. It's a mirror that can change on many pixels the reflectivity, or it can be what is called a DMD, digital micro mirror device that is used in your projector to project light. All these fields are interesting. Why? Because, in fact, the big problem you have when you are doing communication, it may be RF communication or sound communication or optic communication, is what happens in a complex medium. And we live always in complex medium. When you send RF signal in a city or in a forest or in a room, waves are not going in straight line. They are doing multipath. They are scattering everywhere, and it is very complex. And in a room, it is a nightmare. When there are many people speaking in a room, you don't understand anything. And the same happens when you send light in fog. Instead of going in straight line, you see something very diffuse. Now, what happens if you introduce in this medium a reconfigurable intelligent surface? Can we control the wave to improve communication between 2 points or many points or many users? And this is my talk will be on this. In fact, we begin in my lab a long time ago with ultrasound, but with ultrasound, 30 years ago, we have not reconfigurable intelligent surface. And we were interested to do wave control in very complex medium. And for this, we were using not a passive mirror, but we were using what is called active array of antenna. These antenna are piezoelectric antenna. Each of antenna can be a transmitter or a receiver. And the idea we have was the following, because there is a very nice property in waves. It is what is called time reversal invariance. And I will explain what we were doing at this time. We have a medium where we introduce an ugly medium full of obstacles. And we have a source that sends a short click, ultrasound click, wave propagate, it's going in this ugly medium, and now we record what comes from this medium on a set of antenna. And because we can digitize all this signal that we record, we record on each of these antenna the wave that is coming from the unique source, and it is a very long coda because there is multipath, and it is like you have noise. And for everybody, what you record is noise. But because we put this in memories, we can read this memory in a last in, first out operation. That is to say, what we receive, now we will read it by changing the time reversal, the time chronology. We time reverse this signal. Oh, sorry, I made a mistake. And now we will send exactly in reverse time all this signal on the antenna. And now the antenna become a transmitter. And now there is something magic. When you send all this data in reverse time, now what is sent by the antenna come back on the source as a short pulse, as short as what you have said. Signal become very long when you receive it, a lot of reverberation, you send back, it's recompressed. It is like time is going back. And not only this, if you look on what size it's recompressed on a very small spot that you can see here in the red color. And this spot is very thin compared to what you obtain usually with an antenna of this side when there is no obstacle. When there is no obstacle, this antenna becomes like a lens. It gives you a very big focal spot. But when you have introduced this medium, which is ugly, suddenly the focal spot becomes very thin. It is like the medium becomes a lens. And this is a beautiful property of time reversal focusing. When you go through a very complex medium, it is a plus, it is not a minus. Because if you play time reversal, you focus back, and now when you do this, you can begin to do communication. Why? Because instead of sending information to one guy, you can decide to send to 5 guys different kind of information, and if there is an ugly medium, because of this property that the medium become a lens when you play time reversal, you can send 5 different beams, each going on each guy, and you can add modulation, and each guy receive what you want to receive. If you do the same in a medium which is free space without obstacle, you cannot do this because the focal spot is so big that what you send to one guy is going to the other guy, and everything is mixed. You have crosstalk. This is time reversal. And when we have done this 30 years ago, people in optics were very jealous because they say, guy from ultrasound, poor guy, why we cannot do the same? Why they cannot do the same in optics? Because they have not a set of small antenna that they can control with digitizing signal. It is too difficult. And now my colleague in optics in Holland, Halar Mosk, decided in 2007 to try to do the same, but not for broadband signal like what I show, but for narrowband signal. They use a laser beam, and they decide to send light through a piece of paper. When you send light through a piece of paper, light goes through, but what is going out is ugly. It is what is called a speckle. And if you send a laser beam through a piece of paper or through a piece of tissue, on the screen you see random spot, and you know this. And they introduce a spatial light modulator that exists at this time to control as a mirror the reflectivity on each point. And instead of focusing, of sending light which go everywhere, they want to focus light on one spot like we were doing in ultrasound. And they found a configuration of a spatial light modulator that through the piece of paper focus light on one spot. And they can go through fog and just focus on one spot. And it takes some time, it's an iterative process, and after they can do the same, not only to focus on one spot, but to focus on more spots. And they can do this, and they can focus on 3 spots through a piece of paper that destruct light coherence, but they can learn what is the best wave by using spatial light modulator. At this time, we were very jealous of them because we were thinking, oh, this guy found a solution that uses a mirror instead of using active antenna. And we decided in my lab to build a passive mirror for microwaves. And this is the story, and I will show you this a little bit better now. Now, if you want to understand how you can increase what is called Shannon capacity, that is to say the amount of information that you can send from an antenna A to an antenna B. Here I speak of antenna like in microwave. In free space, you know that if the distance between the two is very long, what you send from R when it arrives on B, the signal is very weak, and you have a very bad signal to noise, that is to say, very bad Shannon capacity. Two antennas at 1 kilometer, one from the other, of at 100 meters, are not effective. You need to send a lot of energy from point R, and it's too much energy, and you don't like to use much energy. Now, how can you improve communication between R and B? The best is to live in a room which is an ellipsoidal room, because there is a beautiful property of an ellipsoidal room. It tells you that if antenna A is at the foci of ellipsoidal room and antenna B is at the second foci, when all the waves sent by R are reflected by your ellipsoidal room, all are arriving on point B at the same time. This is the property of an ellipsoidal room. And you have this in Paris Metro, for example. In Paris Metro, the shape of the metro is ellipsoidal. And if you speak at one position here of a metro, and I play with this, the guy which is exactly at the foci hear perfectly what you say, but nobody else hear what you say. It is only this that refocus. And this is nice, but not very easy. You cannot live in an ellipsoidal room to improve communication every day. And this works both for narrowband signal or broadband signal, because it is only a question of time delay. All the time delay between all the waves that arrive on B are in phase. And when you work in narrowband, you can say a sinusoidal wave is what is called a complex number, and all these complex numbers add in phase when you are in ellipsoidal at point B, and this is a good communication system. And the focal spot has a size which is half a wavelength. Okay, this is free space. Now, it is nice to be in a room made to communicate between 2 points. But now, can you imagine to have a room a little bit more complex that make that when a guy at point A speaks to a guy at point B, at the same time, a guy at point C speaks to a guy at point D. If you superimpose two ellipsoidal rooms, but it is not easy for an architect to do this, you can do it. But it will be only part of ellipsoidal room, and guy A speak to B, guy C speak to D, and they are not connected one from the other. And you ask the following: can we make a room like this, not only for 2 by 2 people, but for many people? In real life, you cannot create boundary like this, but you can use digital control if you use intelligent surface. And this is what I want to show you. If you put in a room, in some part, an intelligent surface, can you mimic a lot of ellipsoidal rooms that connect different people, each to the other one? And I will show you this with sound and with microwave. With sound, it is a very interesting problem. It is known as the cocktail party effect. When different people are speaking, it's a nightmare. For me, it is even impossible to understand anything. And you ask, if I have a special room where I can control the boundary, can I make that 2 guys will speak to 2 other guys? There is no crosstalk. You will see that we can do it. Now, you can do also this for RF signal. Imagine that you have 8 antennas here. 8 antennas in room, it's my office, and you want to send to 8 other antennas electromagnetic information. And you have to control the boundary of the room to do this. Can you do this? And I will show you that we can do it. Now, let us come back to the first idea. Just 2 guys. It is called SAICo information. Point A want to speak to point B. But in real life, you are not in ellipsoidal room. You are in room with boundary, with obstacle. And the field is completely random. And typically, the field that you have in a room verifies something which is called relay statistic. And now the idea is, if I put on one part of my room a tunable reflecting boundary, can I mimic an ellipsoidal room? Can I make that all waves coming from R, when they come on the surface, intelligent surface, are reflected to arrive in phase on point B? can I mimic ellipsoidal room? And this is what we have done 10 years ago in our lab. And first, we are doing this in a room where we send information in a bandwidth which is not too big. That is to say, you know that when antenna alpha emit something in the room at one frequency, you have a random pattern. And you can define what is called the coherence length of a pattern. It is the size of each bright spot. But there are black spots and bright spots where you have no light. And you can define also what is called coherence bandwidth. When you change the frequency of your antenna, from how much you have to change to have a new pattern. And this is called the coherence bandwidth. But if we work with narrowband signal, like in 5G, you live in one coherence bandwidth. The amount of data that you send is in one coherence bandwidth. Now, how can I improve things? Mathematically speaking, I want to find for each pixel of my mirror, the reflectivity that I have to put on it. And the reflectivity is a complex number because I send only one sinusoidal wave. And the reflectivity has an amplitude and a phase. It is like a complex number. And I want to find what are the best phase to reflect waves to make all of them interfere constructively on point beta to mimic an ellipsoidal room. This, I will skip this because we have no time to go on this, but this is interesting. And at the end, perhaps we can speak of this because this intelligent surface allows you not only to improve communication, but it allows you to see people in the room. Now, how can I make the connection? If antenna alpha emits, if I receive an antenna beta, I can measure what are called the matrix element of the matrix between alpha and each pixel. And I can find what is the best configuration of my mirror that exactly compensates for all the phase difference between alpha and each element I, and between beta and each element I, whatever is the complexity of the room. And I can find the best configuration to make that what is going directly from alpha to beta plus what is going through the wall, the smart wall, are in phase. And I can do this. Reflectivity, a complex number, it means that you have to control amplitude and phase. It is too much for us. And what we do, we simplify this. We will have only a mirror that is a phase mirror. It reflects light with amplitude 1, but it can change the phase. And we do another simplification, which is the key of the success of our technique. We do only what we call the binary phase mirror. That is to say, it just reverses the signal of the wave or not reverse, phase 0 or phase pi. And you can show that if you have a mirror like this, when you try what are the best phase to go, if the mirror contains what we call many Fresnel zones, which on the surface of a mirror, it works practically as well as a perfect mirror. And this is much simpler. It is a digital control for each pixel. Now, how to build a reconfigurable intelligent surface with binary phase control? If we work on microwave, this was the first technique that we built in our lab on a piece of checkboard. And each pixel is very simple. When a wave is incoming, if it is an electromagnetic wave, if you have a ground plate, you know that the wave is reflected by changing the signal of pi, by changing the phase of pi. But if you introduce what is called a resonator, if you send a wave exactly at the frequency of the resonator, there is a shift of pi over 2, which add to pi. And because it goes 2 times, incoming, outcoming, now if you send a wave exactly at the frequency of the resonator, there is no shift in the reflected wave. And now if you change a little bit the frequency of your resonator by using what is called parasitic resonator with a switch, now you are in the second state. And it is very easy to do this. And we have built this 10 years ago. And from this, we have created a company, Greener Wave, because wave can be green, you will see why. And we can build this in many different range of frequency. And we can build big surface that contain 1,000 elements. each of these elements does not consume any energy. It is passive element. And when you have 3,000 elements, it is like you have 3,000 antenna. But an antenna in physics, it consumes a lot of energy because you have to put energy on it, and there is most semiconductor. This is passive concept where you don't lose energy. And the company is growing very quickly. And now we have done this for microwave, and we have done this also for acoustic surface. And this is with my colleague in Hong Kong, where I spend some time every year. And we design a resonator for acoustic wave, which are small box. And if you change the volume of the box very quickly, it is what is called an NMOS resonator. And when a sound is coming on it, it can be reverse or not reverse. Same idea for sound or for... Now, let us look how it works. First experiment, we do this in the lab for microwave. We have a room where we have an antenna that sends something, and in another room, you have some boundary, and you have another antenna. And you make a learning algorithm that will learn what is the best configuration of your surface to amplify the signal that you receive on this antenna. And you can do this like this. You will see an antenna, and you see a kind of set of black and white spots to improve the field on this antenna, and we move the antenna at a point where there is no energy. And the system learned. This was 10 years ago. And the system learned how to reconfigure the room to focus on your antenna. And it is a passive system that does not consume any energy. You don't need to have 100 antenna. You have only one antenna and one guide. And you can play with this. And of course, now it goes very fast. Now, you can also not only optimize between two guides, but optimize, between a set of antenna and a set of other antenna. This is called MIMO communication. And now we want to change the boundary of the room to improve Shannon capacity. And improving Shannon capacity means that you want to have a singular value decomposition of the transmission matrix where all the singular value has the same value. This is what we call an orthogonal channel, many orthogonal channel. And the room at the beginning is not like this. And we learn this, and we begin by having a singular value of the matrix, which are not good, and the room learn how to be better, and suddenly you send much more information. Now, we will finish by this, and this is spectacular. Now, let us try to do the same in a room for sound. Our role, you have 200 pixels in this room, but at least it will show you how it works. You have two sources of music, and you have two microphones, and you want that one source of music sends something only on one guy, and the other source on another guy. And in this case, you want to find the best configuration of the room to maximize Shannon capacity. This will mean, in terms of physics, maximizing Shannon capacity, it is like the rank of a matrix between 2 by 2 guys, depending on the different configuration. You want to have the biggest rank of a matrix. This means that you want to have an orthogonal channel, and you want also to have minimum crosstalk. That is to say, you want that when listener 1 sends something, it go only, when speaker 1, it go only on each one, on the other guy. And you want to have a matrix which is diagonal. And you want these two things together, and you found an objective function, and you play with this. And now we will play music. We will do this in a room, and we will send 3 music notes as this is Do, this is Re, this is Mi. And now we want to send 2 groups of music, one piece A, CD song, and piece B. And now what we will do is speaker 1 send something in the room. This is the music you send. And listener 1 receive this. And the room, all the boundaries are flat. No. Now you send together what is coming from speaker 2. Now, the poor guy, speaker one, receives the two music, and he's not happy. Now, you learn how to modify the boundary of a room. And now when you found the best way, what speaker one send is going to listener one, and the crosstalk has disappeared. And you learn like this how to send in a room different message at different guy. It is like you have to create two ellipsoidal rooms connecting 1 to 1 and 2 to 2. And here you send only 3 notes of music, do, re, mi, 3 frequency. In fact, you can achieve this result because you have enough pixels in your room to make that you create at 3 different frequencies 2 ellipsoidal rooms which match 2 guys. And you have a climbing algorithm that makes this. And now you ask, is it possible for speech? Speech is not music. Music, you have some frequency, which is narrowband communication somewhere. It's very broadband speech. Speech, when I speak, I send between 30 hertz and 500 hertz. And all this is very complex speech. And my intelligent surfaces usually are relatively narrowband. They can work for some frequency, but they are not narrowband. And we found a new concept. I just give you an idea. That is a generalization of time reversal mirror. You remember, in a time reversal mirror, if antenna alpha send a click, all the elements of my surface receive a signal, and you time reverse and it's come back to alpha. Now, if antenna beta emits something, if you record this on all elements of my tunable surface, the response. If I time reverse this, it's go to beta. Now, can I make a double time reversal mirror that make, when a guy speaks from alpha, what is coming on the surface is going to beta, but for very broadband signal. And now you have to replace each element, each pixel, now is a special device that combines a microphone, a loudspeaker, and a filter, a tunable filter. And if I can build this, and if I can put this in my room, I can speak with a very large bandwidth, and I can make that it go to another guy. And now we are testing this with this small, it's not ready yet, but here you see on the wall a group of microphone, loudspeaker, plus convoluter. And you learn from the complexity of the room what is the best way to connect one guy to another guy. And we are playing with this. And this is related to what is called now for RIS, for microwave, active ultra-wideband RIS, and this may appear in the future. But I will stop here on this. Just what is important is to understand the following. All communication today is based on base station. Base station use a lot of antenna for MIMO communication. Base station use a lot of energy. You know, all the base stations in Europe, they consume 2 nuclear power installation. Just the energy you have to put. And you send energy everywhere. And in fact, what you want is to send energy just where you want to send them. And RIS is a solution not only in a room to improve communication, coming in even from outside, but in city, in the street. And many projects are coming where people want to have a small base station, but to put reconfigurable surface in street to connect different street to other street with this concept. But I would stop on this. I think I have time.
Yes, you are.
Okay. Professor Mathias Fink.
Thank you.